So I wanted to talk you through the steps of computing the electric field at a point using the full formalism of unit vectors. So the first thing that we're going to do here is figure out what the r vector is. So the formula for the electric field due to a point charge is a constant times the amount of charge divided by r squared and r hat. And so the question is, what is this r? So let's draw a little coordinate system here. We'll make this y, we'll make this x. So we're told that the charge itself is located right here on the y-axis. Our coordinates here are 0 and 5.6. We're also told that the observation location, the place where we're interested in computing the field, which is point P, is on the x-axis with coordinates 8.1 and 0. So this is going to be the case the entire semester when we're using formulas of this type. When we're trying to compute the field of some type that's due to a source. In this case, the source where the field is coming from is this charge right here. And the observation location is point P. This r is always going to start at the source and end at the observation location. That's always going to be true. So r will always start at source and end at the observation location. So here, our r vector, which I can put a subscript here to remind me, in this case, it's the r vector that starts at point Q, goes towards point P. I can write that as the vector at point P, the position vector at P, minus the position vector at Q. And that's the same thing as saying that it's the x-coordinate at P minus the x-coordinate where the charge is, I hat, plus the same thing for j hat. So if we plug in numbers here, the x-coordinate at P is 8.1, the x-coordinate at Q is 0, and then the y-coordinate at P is 0, and the y-coordinate of the source is 5.6. So we end up with 8.1 I hat minus 5.6 j hat meters is our actual r vector. Once we know the r vector, we can compute the magnitude. In other words, the distance between the two. So r is, by definition, when you see the triple equal sign, that means by definition, that's equal to the magnitude of this vector. I can compute that using the Pythagorean theorem, so it's the square root of the x component of that vector squared plus y component squared. This is equal to 8.1 squared plus negative 5.6 squared. And I punch in the numbers and I get 9.8473 meters. I'm keeping a couple extra digits here, even though that's more sig figs than I was given in the problem info, just because I'm in the middle of a calculation and I don't want to cause rounding errors. When we report our final answer, typically we'll want to have it be closer to the number of significant digits given. Although in the homework systems, it's a good idea to always give your answers to 3 or 4 digits so that you're going to be within 1%. Okay, so now that we have r, we can compute the unit vector. The unit vector for r, it's the vector that points in the same direction as r, so I'll draw a little tiny vector here. But by definition, it's dimensionless and it has a length of 1. So we can easily compute that by taking the original vector And if we just divide it by its length, that will shrink it down to a vector of 1. So the recipe to get the unit vector is to take the regular vector and divide by its magnitude. So we end up with, on top, we have an 8.1 I hat minus 5.6 j hat, and into both of those terms we're going to divide 9.8473. Notice that on top there's meters and on the bottom there's meters, so the units are going to kind of cancel out in the final answer, and we end up with, and again I'm going to keep a couple extra digits here, 0.8226 I hat minus 0.5687 j hat. Alternatively, what you could do is you could actually find this angle up here, which is theta, and we know that tangent of theta in this case would be opposite over adjacent, so that would be 5.6 over 8.1. You could do an inverse tangent of that ratio, and you would end up with an angle of about 34.658 degrees. And then the unit vector is just going to be cos theta I hat and sine theta j hat, and you just need to get the correct plus minus in front of those. So we can see that our r vector is moving towards the right, which is a plus sign, but then downward, which is a minus sign. So if you found cos and sine of this angle, that would also match these numbers over here. But generally, it's going to be a bit more useful to forego this theta way of computing the unit vector. The method over here, which is taking the vector and dividing by its magnitude, is going to be a bit more powerful and more useful, especially when we get into problems involving integration. So next, we're ready to use our full formula for the electric field. So we have that the electric field at this point is equal to k q over r squared times r hat. And so k is about 9 times 10 to the 9th. We're told that our charge is 29. That little Greek letter mu means micro, so that's 1/millionth, or 10 to the minus 6. So that's going to be 29 times 10 to the minus 6 coulombs, all over the distance squared, which was 9.8473. And then this is all getting multiplied by r hat, which we found was 0.8226 I hat minus 0.5687 j hat. If you evaluate this part in front on a calculator, it turns out to be a plus 2,691.6. This part in front, incidentally, could be negative if the charge were negative. So it's not exactly correct to think of this term in front as the magnitude of the electric field. It is to within a plus-minus sign, but it could be that there's a minus in the charge here, in which case the r hat is not actually in the same direction as the electric field. So you've got to be careful about these plus minuses. Anyway, you multiply that number, distribute it into both of those terms, and we end up with our final answer of 2,214 I hat minus 1,531 j hat, and this is electric force per charge, so it has the units of newtons per coulomb.